Okay, we're moving on, catching up on time. Sean McCarthy, you're also a well-known person here. I think the bio doesn't have to be read, with one little exception.
That's right.
That you just have joined Dolby, I think. And the title, if I wrote it down correctly, is Director of Video Strategy and Standards. Congratulations for this.
Thank you very much.
The title of your presentation, well, it's here, Choosing Encoding Parameters for High Dynamic Range Streaming.
Okay,
Go.
thank you. Thank you. Thank you very much. And Hans, thanks so much for moderating the session. I also do want to stress that although I have just recently joined Dolby, what I'm talking about today is actually independent research that I've done on my own time. No one's paid for it. So what you're hearing is basically just unbiased, hopefully, and you'll appreciate that. So the motivation here is that we all have a lot of experience now in compressing content, SDR content, HD content, SD content. We have experience with MPEG-2, with X.264, and now we're having more and more experience with HEVC. But as we've moved to HEVC, we've actually increased the number of tools that we give to creatives to tell a story. And what the onus is now on us, as people who are creating, distributing the content, is to understand how to use those tools best. So my talk today is to address the fact that we now have two different ways of transmitting from light to code values to light at the display. One's called perceptual quantization, PQ, and the other one is hybrid log gamma, HLG. We also have our traditional way of coding chroma, YCBCR, and we've had that for a very, very long time. We know a lot about that. We also have a new way of coding chroma and luma, and that's ICTCP. And that methodology is motivated by how the eye responds and adapts to light. It uses some principles of vision science about how the information gets accumulated in the retina, in the visual system, to create what we sense as luma or light, and how it gets accumulated and processed in the retina and the visual system to how we understand color. Okay? The motivation for that new space, ICTCP, is to isolate as much as possible that sensation of light from that sensation of color. And that gives us the ability to process content in such a way that when we process color, we don't affect luma. That's the intention. Okay? But how do we actually now tune HEVC so we can deal with all those different variations? And that's what this talk is about today. So the agenda here is I'm going to talk a little bit about the methodology. What did I do? Okay? And then using that methodology, I want to address a couple of important things. I want to look at how does HDR and SDR compare in terms of our sense of lightness, or luma. Okay? Once we've solved that problem, go to the next stage and look at how do the different ways of dealing with chroma, the different permutations, the 4 different permutations, what is the effect in HEVC of those? Okay? And the output of this is to give you actually concrete numbers that you can take home to your workspace and start improving the way you do compression. I also want to look then at compression efficiency. Once we've kind of taken out all the variabilities and made everything kind of on a constant plane, what's the different compression efficiencies? And finally, give you some data about how you should pick the right resolutions, accommodations, resolution, and compression levels to get the best adaptive streaming. So the methodology. The test time content I've used is content you might have seen me present in the past. It comes from Stuttgart Media University. They developed this in 2014. I think they did a great service to the community. What they did is that they created content that was professional quality, professionally shot, professionally color graded, using PQ curves and a good range of luminances, and made it available to the standards communities and to other people who wanted to test tone mapping and color grading algorithms. I'm using actually 4 sequences, and one of those sequences I'm using 2 different versions. I'm using the light show, the carousel, the fireplace, and Showgirls 2. There's Showgirls 1 and Showgirls 2. Each of those is HDR and PQ. Showgirls 2 is also provided in an SDR version. So we have an SDR baseline or ground truth that we can use to look at HDR content. This is the workflow, and this is, I wish I had the hardware that we just were presented with recently. This is actually quite a bit of time to create a workflow in MATLAB to go from the upper left corner there where it says start here. That's the content that's provided by the Stuttgart Media University. And convert that into 4 different versions, which are in the middle there: YCBCR PQ, ICTCP PQ, ICTCP, and YCBCBR for EHLG versions. I then took each one of those, so it's a sequence, it's a video sequence, and then ran it through x.265. So I did conversion from 444 to 420. I did the dequantization from 16-bit down to 10-bit. Ran it through x.264, ran it through the decode, reversed the process, and created reconstructed versions. So I can then take the reconstructed versions and look at the original content, go back to the original content. It's all reconstructed to the original upper left-hand side there, the the RGB PQ. Okay. What we find is that when we start compressing content, we see differences. So on the horizontal axis here, what you see is a CRF value. A CRF value, for anyone who uses X265 knows, that's the parameter value that you put in the command line for what they call constant quality encoding. It's a parameter that basically is analogous to QP, which is the compression or quantization level or precision level. But and within the X265 algorithm, it's moderated so that you kind of get constant quality over time and hopefully constant quality across different pieces of content. So I use values of 24, 27, 30, 33, and 26. And you see the corresponding bit rates there. So one thing you notice is that the YCBCR PQ has the lowest bit rate, and the ICTCP HLG has the highest bit rate, and in between there, the other variations are pretty close to each other for overall content, okay? What I found very interesting is that when I actually converted the content from the chroma content to just black and white, the achromatic content, all of the curves, all the efficiencies were basically the same. So what's it telling us something pretty profound is that the differences that we're going to see in these different permutations of HDR have to do with the chroma, mainly. Okay? Before I get into that and explore that a little bit more, I want to actually look at something else that was also very interesting to me. So when you look at the SDR version of Showgirls 2, remember that, and compare it to the HDR version of Showgirls 2 for the different permutations, all the different permutations Showgirls 2 for HDR are basically the same when it's achromatic. When you look at the achromatic SDR, you see actually a much higher bit rate at the same CRF values. And that's very interesting. So the first question is, why is that the case? And the reason why we need to find out why that's the case is because we want to be able to treat SDR and HDR as an equal playing field, apples to apples, when we're doing streaming media. So why is that the case? So what I did is I plotted the values in the SDR content versus the values in the HDR content. And this is going to take a little bit of explaining, is that the horizontal axis here on the left-hand side are the range of pixel values, 64 to 940, for the Luma component of SDR, Rec 709, okay? And then for each frame in the Showgirls 2 content, I found every pixel location that had, for example, a value of 512. Took those pixel value locations, and in the HDR content, I did the average value of those pixel values, okay? And they're not going to be exactly the same. So there's going to be an average mapping from from SDR to HDR. And that's what you're seeing in that colored curve there. And that colored curve is actually two different curves. Is that curvy curve. That's the Y prime and the I for PQ on the left-hand side, and the Y prime and the I for HLG on the right-hand side. And there's lots of similarities. The most important thing that I want you to take home from this is that you'll notice that the range of values that are used for the Y and the I is smaller than the range of values that's used for HDR, is smaller than the range of values that used for Y and I for SDR. And you can see that if they were the same, they would have followed along that dashed black line, okay? So the hypothesis is that the reason the SDR bit rate is higher than the HDR bit rate for achromatic content is because there's actually more values in the range that are being quantized. So there's two ways of looking at that, to testing that hypothesis. One of them is to just artificially lower the contrast of the SDR content. So basically it's just in MATLAB, just lower the contrast. The other one is actually to change that CRF value. As I mentioned before, that CRF value is equivalent to or analogous to QP. And QP is the parameter that tells us how many quantization levels, or the precision of quantization we'll have there. Lowering the CRF value basically increases the precision of quantization in HDR. Okay? So to test that, I did this. So by lowering the contrast, basically what I did is basically just did a linear regression fit on the Y and I content, and then multiplied all the values in SDI by that, and then recompressed it, and I find that, in fact, yes, that's an indication that hypothesis is correct. That's the range of values, which is most important there. Doing this here is also, you can see, if you slide that SDR curve over by a CRF value of 2, you overlay, in fact, the HDR content. So here's the first tuning parameter for HDR. no matter what variation of HDR you're using, whether it's PQ or HLG, ICTP or YCBCR, you should actually use a CRF value or a QP value that's 2 lower than you would have used for SDR. If you do that, you will get the same curve in terms of the constant quality parameter for X265 and bitrate. And in that case, all of those variations, including SDR, are equal. They all basically have the same compression efficiency if you're doing achromatic only. If, however, you're looking at chroma, the story is different. Here I'm showing the same information I showed before, a snapshot or a slice of the information I showed before, where I showed that there was 2 different curves having different bit rates for the same CRF values for the different permutations, and they were based upon chroma. Here I'm just showing it for a particular CRF value, a CRF value of 27. And what you should notice is that on the orange columns on the left-hand side, each of those is one of the 4 permutations. And the orange column is the achromatic value. So those are all basically the same. But the chroma component is more and more. So the contribution of chroma to the total bit rate is dependent upon the HDR permutation. Okay? So the question is, why is that the case? Before we get there, and again, trying to link HDR to our knowledge of SDR, if you look at the contribution of chroma to total bit rate in SDR over this kind of content, over the showgirls content, I'm sorry, showgirls 2, you find that, in fact, about 8% of the bit rate is due to chroma rather than the achromatic component, rather than the luma component, okay? It's the same percentage as if you had used ICTCP PQ, which is telling us basically that if you had taken ICTCP HDR and SDR content and simply done that achromatic shift, the CRF -2 on the SDR content, you would have an almost apples to apples drop in equivalence, okay? However, we've seen that the percentage of chroma contribution for PQ YCBR and HLG YCBR is smaller than that, and for the ICTCP, it's a mouthful, HLG, it's larger than that, okay? So again, taking inspiration from what we saw for the luma components and ranges, we take a look at here. And then again, this is an eye chart again, but so the top row is for either the CB or the CT. So CB on the left, A and B, CT on the right, C and D. On the lower row, same thing. We have CR for E and F and CP for G and H. And then the first and second column are PQ, the second and fourth column are HLG. What we're showing is that on the horizontal axis is, again, the values of the chroma for each one of those components in showgirls 2 color. This is overall, I'm sorry, overall. And then on the vertical axis for the different permutations. I'm sorry, the lower value is for the horizontal value, I'm sorry. This is for showgirls 2. The horizontal axis is for the SDR version. The vertical axis are for the different permutations of HDR, okay? And what we see again, for example, in A, you see that if the chroma range had, and the average values had mapped 1-to-1 between the SDR and the HDR, we would have fallen along that straight diagonal line, that black line. But in fact, what we find is that the range of values in the HDR version are much, much smaller, and that's shown along the vertical axis. There's a much smaller arrow. And again, with the orange border I've drawn around the third column there is showing that, in fact, we saw that the contribution of chroma to total bit rate for ICTCP PQ was similar to what we see for SDR. And we see, in fact, that there's the greatest linear correlation in that situation as well, which kind of makes sense. So given this being the hypothesis that it's the range of the values that occurs in these different permutations that causes the change in the contribution of the chroma bit rate, what can we do to change this? And so the objective is we want to actually have all these things be apples to apples in terms of X265, and then we can start comparing other things. So I've actually ran across some work here. Jason Strom and some other people in Picture Coding Symposium 2016 had suggested that using chroma quantization is a good way to start dealing with these kinds of issues. It wasn't particularly for this kind of issue, but you could actually make a very easy extrapolation from their suggestion. And so that's what I picked up, and I did that. And I said, let's use Chroma QP offsets And by using Chroma QP offsets, we can change the precision by which we're actually encoding the chroma component. Okay? So that reduced range of chroma values in the HDR values can be quantized more precisely by changing the Chroma QP offsets. Chroma QP offsets is a parameter that you can put in the command line for X265. And again, I'm using X265 because it's open source, it's unbiased, it's not promoting anyone. But you can use these same principles in your professional encoder or any other encoder you're using. Okay? So the way I did this is I actually did a linear regression line for each one of the variations, for each one of the components, the CT, CP, CB, CR, against the SDR content for showgirls 2, took a ratio of the slopes. And the ratio of the slopes then gives me basically a relative precision by which I need to equalize. I then used the well-known fact that if you double the quantization parameter, the QP value, and CRF value is similar to the QP value, you will, actually a change of 6 is basically a doubling of the precision, a doubling of the bit rate. So I use that equation that you see at the bottom of that table there. And I use ICTCP PQ as my baseline, but I could have picked anything because the relative changes in this, the Chroma QPs doesn't matter about what I use the baseline. I picked that one as my baseline because that was most similar, again, to the SDR, if you remember. Okay? And so on the far right-hand side here on this table, the 2 columns there, those are the QP offsets, Chroma QP offsets, that this methodology suggests I should use. When I applied that to the content, so put those in the command line parameters to X.65, and ran the results again, I got this, which was very, very satisfying, is that now SDR and each one of my 4 HDR variants has the same contribution of chroma to the total bit rate and the same contribution of luma to total bit rates. So now they're all apples to apples to apples. If I had also added that CRF -2 that we had talked about before for luma, each one of these bar graphs would have been basically the same. So the luma and the chroma components would have been straight all the way across. So now we have a situation by tuning X265 where SDR and our 4 HDR permutations are all equivalent in terms of how many bits they're using for a CRF value, the constant quality value, and what percentage of that total bit rate is due to chroma, and what percentage of that total bit rate is due to luma. Having now that equal playing field, that ground truth, we can start looking at other things. First off, it's very interesting to me is that when you do Chroma QP offsets, you're doing more than equalizing the playing field. You're actually creating a better mix of bit allocation to chroma and luma, and that's what's shown here. This is for ICTCP HLG. The gray curve, which is further to the left, is after the Chroma QP optimization. The blue curve is before it. That's basically equivalent to a reduction of 5 to 10% of bit rate for the same quality. Quality here is actually being measured by a metric called TPSNR, which is a transformed PSNR. I use 2 metrics in this paper. One is TPSNR and one is PSNR DE2000. Both of those are open source metrics that have been used in the past. They were in fact used by the MPEG committee as the basis of doing evaluations. So I just adopted those rather than doing something fancy. A lot of you who are experts in video quality assessment know that neither of these metrics is a direct predictor of subjective video quality, but right now they're kind of the best we have as open source available metrics. Now looking at, on the horizontal axis is bitrate again, and the vertical axis is the PSNR. So now in each case I've compressed content with a certain CRF value, I've looked at the average bitrate over that clip, calculated the PNR value over that clip, and what we find is that we have a clustering that basically YCBCR PQ, YCBCR HLG, and ICTCP PQ, all kind of really similar. Maybe 5–10% difference between them. But with TPSNR not being a fully fledged quality metric right now, you know, just look at the trends, I think is the most important thing. The ICTCP HLG tends to be kind of the laggard here, and I'm not quite sure why that is. I'll show you another graph where that's not the case. In this case, if you had to pick one, it would be ICTCP PQ kind of is higher on this one. For this test content, and again, you have to look at lots of test content besides what I'm doing. So part of what I'm giving you here today is data and recommendations, and part of it is a methodology that you can take home and start using yourself. When we look at that other metric I mentioned about PSNR DE2000, we get much more close results. Again, they're all kind of very much clustered. You could argue for D2000 that the ICTCP PQ is a little bit better, and it could be actually significantly better. Just want to remind you again, I'm at Dolby now. This looks maybe a little bit self-serving, but this was all written and delivered to SMPTE long before that ever happened. So now I want to switch back. Now, how do you make choices when you're doing adaptive streaming? Because of course, when we're delivering content, we're not just delivering one bitrate all the time anymore. We're in a world where we need to modulate bit rates and resolutions and maximize our experience, the video quality. There was a project I was involved with a number of years ago that was actually started by AT&T and some others, and it produced this ATIS 08000061 methodology for doing that kind of thing, making those choices. And the idea is that if you look at a distortion versus bitrate graph, for different resolutions, you'll find that the curves tend to cross, and that's what you can see here a little bit. If you look at the gray and the orange curves, they tend to cross that blue curve. And that point at which they cross is kind of your indicator that it's time to switch your resolutions, time to kind of down-res your content, because by down-resing your content, you actually get better, less distortion, okay? And so this is just basically the metric. When you look at it, you see some themes. One theme is that there's not a huge difference between going from 1920 by 1080 down to 1280 by 720 or 960 by 540. So that 1280 by 1280 by 720 and the 960 by 540 are kind of overlay each other a little bit. And if there's a difference, it's probably not enough to really care about. That, I suspect, is actually an artifact of the content I've used. And as we use more and more complex content, I think we'll start seeing more separation between those kind of things. The other one is that for PQ content, your switch point kind of is a little bit lower. It's about 500 kilobits lower, which means that you can keep on pushing bitrate down at the higher resolution, which might be good for your customers. With a PQ, then it looks like you could do with HLG. Again, content dependent. I used 4 test clips here. Methodology should be replicated to see if this actually true is a universal truth or it just happens to be the truth for this particular content. Okay? And then one caution. There was I think it's known that there's the color volume is really what we're talking about here. It's really hard to always explain it, try to describe it. But when you're looking at color volume, particularly when you're doing transforms, when you're going from HDR to SDR, SDR to HDR, the different variations, HLG, PQ, and then using this new Chroma thing, you can actually get to situations where you get out of range. And I won't say out of gamut, you're out of range. Just mathematically, your processes actually pop you out of the ranges that are acceptable ranges in the standards. And that's what I'm showing here. And often they're very, very subtle. I'm not sure you can see it here. But if you look at that circle there, so A is the original content. B, on the upper right-hand side, is the ICTCP HLG version of that content after the transforms. Around those lights, I think you'll notice it's a little bit desaturated. There's like a little bit less color, maybe it looks a little bit brighter. It's a very subtle thing. If you do A, B, it's obvious, but I think a normal viewer might not notice it. I actually calculated the number of pixels, what percentage of pixels was affected by this artifact, and that's shown in the lower graph there. So for content like Carousel Teaser, which is really pushing the HDR storytelling mode, you get about 7%. For more normal content like Showgirls 2 teasers, it's like basically 0%. And Fireplace, which has very vibrant fire, it's about 1% of the pixels. It makes a difference on. Okay? So here it is. So hopefully this is understandable and very, very practical, and you can use this stuff. You can read the paper. It has all these details in it. The conclusions are that if you want to put HDR and SDR on an even playing field, you should use a CR value or whatever is equivalent in your encoder that's 2 less than you would have used for SDR. Okay? For Chroma, you should apply Chroma QP offsets. And the reason to do that is because the natural way in which these formats work represent chroma and different range values, although we use the same range value for all the different permutations. These are good starting points. Again, methodology is king. Use this methodology, go figure it out on your own content for your own needs. But this will give you an equal playing field. Those 1 and 2 will give you an equal playing field across SDR and all the HDR permutations. In terms of compression efficiency, again with a caveat for the content that I'm looking at here, which is a very small set of content, the ICTCP and any kind of YCB-CR are very close, and you can use any of those. And then for adaptive streaming, using this methodology combined with that ADIS methodology, it looks like about 1,500 kilobits per second. So you're going here, this is 1920, 1080, down to a lower resolution. You should repeat again this methodology if you're talking about 4K HDR, where are your switch points there, okay? And there's no clear benefit right now for that lowest resolution, the 960 by 540, content dependent. So thank you very much, I really appreciate it, and Hans, thanks again.
Here we go.
Okay.
Here we go. You have
Hey, Sean.
Hi, how you doing?
As you know, I manage X265. Did you take a look at our HDR optimization feature in X265-HDR-opt?
Oh yeah, I did. I didn't use it because it was labeled as experimental when I downloaded the X265 build. So, yeah.
Okay, so that, that feature implements the recommendations of an MPEG study group. I think we'll make that feature non-experimental very soon.
That would be great, yeah.
I mean, basically, it implements those optimizations that have shown up to 28% higher compression efficiency for high dynamic range content. So
yeah, no, and that would be great to have it, especially open source. And I think that's the point, is that I'm showing one bit of the steps towards optimization as a practical role. And I think this is a point you made very well yesterday at our pre-meeting. It's really nice to see us in a world now where we're talking about what do we have to do in terms of practical things to make HEVC and HDR really successful in commercial applications. And I think what you're talking about is one of those things.
well, I look forward to following up with you and with any purveyor of high dynamic range standards to optimize X265 for each HDR standard.
Great, thanks.
Thank you.
Yep.
Thierry.
Hi, Thierry.
Hello, Sean. Thierry Fautier from Harmonic. So, Sean, first, thank you for sharing all your insight. And this is, we can always debate on PSNR versus VMAF, and I think there will be other topics, so I'm not going there. I just wanted you to share your perspective on what you found in your explorations or research versus the MPEG to be published cookbook on HDR encoding. And I assume you have read it?
No, I have not read that yet.
Okay,
so am I reproducing what they've done, or?
Well, I think they have been working very hard on all those aspects.
Okay.
What are the quantizer scales? What are the artifacts? What are the type of measurement they saw? And this will be, I think, published at this current MPEG meeting. So for all those interested, there is an MPEG task force on how to encode HDR with HLG and HDR10. And I think it's good if you can
so if this independent research has no value other than to validate what they've done, or be another external source?
It's always interesting to see from different perspectives what people observe, measure, because I think the devil is in the detail based on my 25 years in video compression.
Excellent, yeah.
Good morning. Hugo Gaglioni from Sony. Congratulations, a very impressive methodology in research. Similar to the previous question, you are using codecs. All the codecs that exist today have been designed by people watching SDR images. All the coding strategies, quantization, characteristics, VLC tables, motion projections, everything has been done watching SDR. When you apply that codec to HDR, everything goes through the window. Then the artifacts produced by having the strategies based on SDR encoding completely override the effects that you are producing. Therefore, right now, and it's a very complex process, to optimize, we are optimizing intra-frame techniques right now for HDR. Optimization of inter-frame techniques is incredibly complex. But the benefits are much more consistent and measurable than those values that you produce only on the estimate of Chroma.
I think those are very excellent points, and it points to that we're in a world of how do you measure subjective quality in HDR. We don't have good tools for that.
We don't have those tools.
Yeah, Thomas Ederson Fox, great data.
Thomas,
so I was going to ask the question, are there any projects in the industry to create objective measures of quality for HDR that will match up with the subjective experience of HDR? Because obviously, when I'm looking at HDR, I'm looking for things like if I see lightning bolts or fire, I'm expecting a completely different experience from SDR. Are there any projects to try to come up with these useful objective measurements for HDR?
Yeah, I think there are, and I think one of the most interesting things is, so Alan Bobrick, University of Texas, is always very active in this area. I think there's a number of discussions at this meeting, I think they're today about quality. I think though, when we get to content like HDR, I've got 6 seconds, there's other things like empathy. So like probably Chrome at Dolby is looking at, what happens when someone feels fire. They're not seeing fire, they're feeling fire when they're looking at it. And there's things like machine learning we heard about on Monday, like VMAF and that sort of stuff. How do you use everything that we know in an automated way to make better results? Sorry. Yeah.
Craig Todd, Dolby.
Okay.
There have been proposals that SDR compresses better than HDR. Therefore, a more efficient way to deliver HDR would be convert it to SDR, deliver it, and then convert it back to HDR.
Right.
Does your evidence give any support to that scenario?
From the content I have, so the idea is that let's create HDR in a way that you can think of it as a backwards compatible version, and all the HDR stuff gets added, and you get that same experience. From what I'm seeing right now with X265, we have, basically you can put everything on an equal playing field, and then the question doesn't become, is it more efficient or not, is which metric are we going to use to actually measure quality, right? So does that answer your question?
Well, do your results indicate you could save bit rate by sending HDR as SDR or not?
No, it wouldn't be saving bit rate. It wouldn't cost any more either, so.
Hi, hi, Marcelo Bertolmeo from University Pompeu Fabra. So if I understand correctly, the TPSNR measure uses the PQ as the nonlinearity.
Yes.
Do you think that biases the result because you're using the PQ nonlinearity to evaluate the PQ-based distortions?
As a scientist, I'm going to say you have to keep that possibility open. PQ is designed for static viewing in a way, and so it's an area that should be investigated and resolved. Okay.
Thank you.
Sure.
Last question.
Hi, Alan Stein, Technicolor.
Hi.
Following up on Craig's thought, one of the concerns with using X265 and the CRF parameter is that it actually introduces rate control into the equation. It doesn't keep a constant QP.
Right.
The content that you used, I believe, have no scene cuts, they're 24 frame, and they're all 4,000 nit?
Yes, that's right.
So, okay, so I think, do you have any thoughts about trying things at 60 frame, trying things at a variety of peak luminance? Also, the second part of that is it all within P3? Does it extend beyond P3? Is some of it 709? How much, you make conclusions about Delta Chroma QP, but how much of the chroma space is used?
I'm not exactly sure of the chroma space. I think the important point here is the methodology part again. So scene cuts, all that stuff, different kind of content. Methodology can be applied to it. Maybe throw the methodology out if it doesn't work, but the results are what the results are. So,
Thanks.
okay. Thanks so much. Appreciate it. Sure.
Thanks a lot.